Okay, let's get started. A couple of administrative items to begin with. First of all, just a reminder the problem set 7 is due Tuesday. Second of all, I announced a couple lectures ago that I would give extra credit points for corrections that people came up with in class, so they made a mistake on the board. Someone sent a correction via email to the slides from our lecture on Thursday. I'll point out the correction in a moment. I'd like to reward that too. That's even more important than catching mistakes on the board. So 2 extra credit points for the person who sends corrections to slides. They're non-trivial. You know, if I forget an apostrophe or something like that, I may not give an extra credit point. And if all of you send me a correction, I may not give everyone extra credit either. So I'll sort of be the ultimate arbiter. But certainly, if you spot problems with the slides that are online or in class, I'd like to know about it. Okay, so questions about administrative stuff before we proceed? Okay, let's get started. I'd like to finish up a couple. What we did last time was to really finish up the work we were doing on developing a theory of supply. So we started a few lectures ago now with a description of the firm's problem. We talked about how a firm could minimize costs for any level of output, how they choose a level of output, and we put those things together last time to talk about how a firm would respond to the prices it faced, prices for inputs and outputs, and choose some optimal level of output to produce. So that gives us a supply function for the firm, and which is a very useful object. I'd like to say a couple more things about the firm's supply function. In particular, I'll talk about the supply elasticity. That'll be a familiar-looking kind of object, analogous to demand elasticity we worked with before. I'll talk briefly about how supply aggregates, and then I'd like to turn to sort of an application, if you will, which has to do with supply for firms in extractive industries, which I think you'll find interesting. And there'll be kind of an example involving oil firms that I'll hope to get to before the end of the lecture. Okay, so before we start, here's the example I said has to do with oil. So here's a quote from John Rockefeller. He's really talking here about production functions, I think. So he says, "I'd rather earn 1% off 100 people's efforts than 100% off my own efforts." So you know, this is Rockefeller. Excuse me. Sorry about that. Rockefeller, of course, is one of the great industrial titans of the 20th century, and was one of the beneficiaries of changes in technology that allowed manufacturers or oil producers to take advantage of sort of large-scale specialization in their labor force. Yes. Oh dear. That's probably a consequence of. Let's see if we can bring back John D. Oh dear. Having lots of electronic problems this morning. Bear with me, please. Is he back? There he is. Okay, good. This is not back now. Okay, there we go. Okay, I think we're ready to proceed. Okay, so the quote refers to the idea, or at least I interpret this as referring to the idea that there are returns to specialization in labor. So we had a quote from Adam Smith a few lectures ago that bore on this also. And an example relating to Adam Smith's pen factory, which you probably are familiar with. Actually, who's not familiar with the pen factory example? Okay, so early on in The Wealth of Nations is a very famous example that Adam Smith gives. I really ought to have a quote here for you, but I haven't. And what he talks about is the idea of the manufacture of pens, you know, sort of straight pens you might use in a sewing project. And so this is, you know, Smith is writing in 1776, and sort of, you know, still, you know, the Industrial Revolution is underway, and he's comparing the labor that goes into the manufacture of a single pen. So if you went to a blacksmith and said, "Make me a straight pen," there's a whole bunch of tasks that person would have to do. They have to go and get the ore in an appropriate way. They have to draw out the wire. They have to cut it. They have to hammer a little head to the thing. They have to sharpen the end. And he provides an estimate of how long it would take a single person to make a pen, or a dozen pens. He says he thinks one person working could maybe make, you know, 20 pens a day or something like that. I can have the exact numbers for you. He compares that with an actual pen manufacturer where they're doing all the same tasks, but they've divided up the tasks sort of according to different people. So there's one guy who's in charge of getting the metal ready. There's another guy responsible for drawing out the wire. A third guy who's responsible for chopping up the wire. Another guy sharpens it. Another guy puts on the heads and so on. And so he observes an actual pen factory that employs a dozen people or something like that. And the total output, even though you know, it's 12 times the amount of labor going in anyway, so it's 12 people instead of one person per day. Their production of pens is, you know, many times, you know, order of magnitude or more greater than you expect. So these are what he calls returns to what we call returns to specialization. And so a little bit later, we see Rockefeller as one of the other beneficiaries of this. So he's in charge of a sort of operation related to oil in his case that involves capitalizing on specialization of hundreds of workers. And as he says, he'd rather have 1% of the returns to their labors rather than 100% of his labors. Okay, so let me go ahead and turn to some discussion of supply elasticity. So you'll recall we had a supply elasticity last time. We talked about the firm's supply function being a function f of PW. So this is supply. We just defined it this way. And when we talk about the supply elasticity, you know, there's different things that can enter here. We might think about how supply changed when we change input prices, but if we don't specify, and that's something we compute, if we don't specify and just say supply elasticity, we'll typically refer to the elasticity with respect to the price of the good, that's price P, that the good is sold for. So you'll recall that one formula for the elasticity is the formula we give here. So I'm going to call the price elasticity here the Greek letter epsilon, just equal to the partial derivative of the supply function with respect to P times PW, P divided by Y, or it'll be P over FPW if you prefer. And so that's an expression we can use for the elasticity at a point of the supply function. So here's a graph. Here's the kind of graph we might have of this thing. If we have supply Y, price P, some kind of supply function like this, the elasticity graphically is the derivative. You know something? Let me do the reciprocal of this. So I'll have prices here and output here. So this will be output y in this case. So we'll have here the slope of the function, something like this. This is df dp. The elasticity is not this slope exactly. Instead, it's the slope divided by the slope of a ray that passes through the origin. This thing, of course, has, you know, this is the output y. This is the input price p. So we divide this thing, dividing this thing by the slope of this ray gives us this formula for the elasticity, df dp, all divided by y over p. All right, and then if we flip back into sort of the Marshallian price space, we take the inverse of that. And we just have, you know, the slope of this is 1 over df dp, and so we divide by, we multiply by p over y. We multiply by, p over y. But that's because what I've got here is this slope. In this space, look, the axis is shifted. This is the inverse supply function. So the slope here is 1 over this thing, and the slope of array here is p over y instead of y over p. Yeah. So we just need to be careful about which space we're in. When we talk about the elasticity, it's most natural to think about slopes in this space, but of course Marshall has to use the space ordinarily. Okay, let me maybe give an example of a price elasticity for the supply function we've been working with. So I'll remind you from last time that we worked out an expression for firm supply using a Cobb-Douglas production function. And so from that example, we have f of pw, which is equal to a factor. Oh dear. Let me go this way. A factor alpha 1 plus alpha 2 over this old constant involving alphas h alpha times t to the alpha 1 plus alpha 2. This thing raised to the 1 over alpha 1 plus alpha 2. I'm sorry, no, 1 minus alpha 1 minus alpha 2. This thing times a factor a sub I divided by w1 to the alpha 1, w2 to the alpha 2, and this thing raised to the same power, 1 over 1 minus alpha 1 minus alpha 2. So that's a version of the supply function that we derived last time. What I had on the slide last time, I mentioned earlier that somebody emailed me about the mistake in the slides. The error there was that this part, I had the bracket in the wrong place, basically, so it looked something like that. So that's the correction. We should have this form instead. Okay, anyway, so that's the supply function. We can use that thing to go ahead and compute the supply elasticity in a straightforward enough way. We can do it here by just applying this formula. So first of all, let's think about what df dp is. Anyone help with that? So p only appears one place. It's here. So a bunch of stuff I can just treat as a constant. Maybe I'll just put that over there. So I'll have a bunch of stuff which looks like alpha 1 plus alpha 2 over h of alpha, all raised to the, all right, that's the same power, times a, w1, alpha 1, w2, alpha 2. This thing all raised to 1 over 1 minus alpha 1 minus alpha 2. That's the constant part. And what else do I have? Good. So, yeah, so I've got this thing. So I'll have alpha 1 plus alpha 2, 1 minus alpha 1 minus alpha 2, all times t to the alpha, we need to be careful here. So it's alpha 1 plus alpha 2 divided by 1 minus alpha 1 minus alpha 2 minus 1. But this exponent can be simplified quite a bit. This just becomes 1 over 1 over 1 minus alpha 1 minus alpha 2. Is that right? Or no, sorry, minus, hold on, that's completely wrong. It's minus 1. So this gives me alpha 1 plus alpha 2 minus 1 plus alpha 1 plus alpha 2. So I'll have 2 alpha 1 plus alpha 2 plus 1, all divided by 1 minus alpha 1 minus alpha 2. Is that right? This should be minus 1. This part's right? That's uglier than I expected it to be. Okay, anyway, let's bear with me here. So that's df/dp. Yeah, okay, I see. Okay, I think that's right. So this is df/dp. We multiply this thing by y, that is by this thing, and divide it by p. So we can first of all, so we can do it this way. We multiply by, oh, I see. We multiply by p and divide by y. And did somebody earlier try to correct me when I put this expression up here? So whoever said that I had these backwards earlier was correct. Was that you, Hillary? Yeah. Jeff, could you give Hillary an answer credit, please? Don't be afraid to be more persistent next time, Hillary. Thank you. Okay. All right. So I want to multiply all this stuff by py. So let me go ahead and just write that this way. Okay. So let's take care of our p. We've got this p that we're going to multiply through here, which gives us back the plus 1 that we had before. So then we're going to divide by y. So y involves all these terms. So we'll be left with alpha 1 plus alpha 2. Divided by 1 minus alpha 1 minus alpha 2. We get back these terms, and that's what our production was. So this is, in fact, equal to the expression we want. That is epsilon. Okay, is that clear? Yes. It's a definition of the elasticity, which I stated incorrectly here. So the elasticity, let me just rewrite it on a clean slate here, maybe. So the expression I want for the elasticity is epsilon equal to df dp times p divided by y. Or if you prefer, that's equal to df dp times p divided by f of wp. Same thing. Okay, so one thing to notice, okay, actually, that is the question. So this is the definition. So the only thing we need to do then is apply this thing. So I did it in a way which involved a little more algebra than necessary, maybe. Here's df dp. That's that first line there. It involves, So let's df dp on the top, and then I multiply times p times y. Here, multiplying this thing on top by p gives me back this plus p, but then that gives me back an expression which is just the same as the original output, except for this term here. So when I divide by y, it's only this piece that's left. Is that, yes, yeah.
Do they always only depend on the output, or are they allowed to depend on anything?
No, so good question. So for this Cobb-Douglas case, we have one of the features of those production functions is they have so-called constant elasticities of substitution. And here's an elasticity and it's constant. It just depends on these alphas. In the more general case, the elasticity, the y's wouldn't all cancel out perhaps, so it could depend on the w's or on the a's or what have you. So this is a special feature of this class of production functions. Okay, other questions? All right. Okay, so here's the elasticity for the special case of Cobb-Douglas. And you should be able to guess how this extends if you have more than two inputs, right? If you had three inputs, we'd have alpha 1 plus alpha 2 plus alpha 3 divided by 1 minus alpha 1 plus alpha 2 plus alpha 3. Here's another case to consider. What if we had constant returns to scale? What's true of the alphas for the constant returns to scale case in Cobb-Douglas? They should sum to 1. Does that cause problems here? Yeah, so that's we have 1 over 0, which is undefined. We sort of wave our hands a little bit and say, well, if it's close to 1, whereas it goes to 0, then this thing goes to infinity. In the constant returns to scale case, you may recall from last time that in the Marshall space, supply functions are flat. They don't depend on y at all. And so as a consequence, this is for alpha 1 plus alpha 2 equal to 1. And so we sometimes call this, we might call this supply function perfectly elastic or infinitely elastic for sort of reasons that are obvious from this. And the intuition is this, with constant returns to scale, the firm doesn't really care what value of y it produces at. It can produce a little bit or a lot because returns are constant. They'll earn the same profits competition. So if you increase prices a little bit, you can imagine the firm could respond by increasing output hugely to try to take advantage of that small price increase. And conversely, if you lower prices a little bit, that'll drive output to 0. All right, my slides are going back to sleep here again. Let me see. Okay, so that's supply elasticity. Any other questions about that before I go on? Yes.
So the A1 and A2 is for different input ratios?
Yeah, I'm sorry. So this is still for the Cobb-Douglas production function. So these are the exponents associated with that. So this is for a production function. Keep losing my chalk here. This is for a production function y equal to a x1 to the alpha 1, x2 to the alpha 2. Yeah. So this is the constant returns to scale case. And recall last time we sketched out a bunch of different possibilities for firm supply corresponding to different possible values of alpha. So the key case to consider were constant returns to scale, increasing returns to scale, decreasing returns to scale, and then also it turned out that having alpha equal to some of the alphas equal to 1/2 also was sort of a special point. Okay. All right, I'm going to return to that special point in a moment. I want to think a little bit about aggregate supply here. So aggregate supply is simple in a way. In the same way that aggregating demand for consumers was straightforward. You just take demand for consumer 1, demand for consumer 2, demand for consumer 3, and so on, add them all up, you get aggregate demand. The same thing holds for aggregate supply. So we know how to work out the supply function for a particular firm now. For any firm with a Cobb-Douglas production function, we can give it a very explicit expression. For other production functions, at least in principle, we know how to solve the maximization problem and characterize the solution. And then you just add them all up. So I called aggregate supply here this number big Y, since it's aggregate instead of individual. And it's just going to be this aggregate supply for an industry within firms will just involve summing up the supply over each of those firms individually. So maybe it's worth having a picture of that. Let me get rid of this perfectly elastic supply curve for a moment. So let's suppose we had a supply curve for a firm that looked like this for firm 1 and another that looked like this for firm 2. Okay, so there's two different perfectly good supply functions. Both of those wouldn't come from a Cobb-Douglas production function because of this constant here, but they're perfectly good supply functions. So graphically, how do we add this up? How do we match this? Exercise on the board of doing a summation. How do we compute aggregate supply across these two firms? Yeah, remember our axes are kind of backwards, so instead of summing up this way, we'll sum up the y's this way. So graphically, you can think about this. Pick a level of P, or start with P0 maybe. At a level of 0, what's aggregate supply? 0. If we move price up a little bit to say here, what's aggregate supply? Yeah, firm 1 is producing, firm 2 is not. It's still producing 0 at this point. So aggregate supply just follows firm 1 supply function up until what point? Yeah, very nice, I like the line. So the point where firm 2 enters production, where they start producing a positive quantity. Exactly. So we'll go up to this point right here, and then that'll induce a little kink in the aggregate supply curve. Once we get to this point, we'll have 2 times this amount of stuff. So we'll get something like this, and then as you increase prices up here, we'll have this plus this. So we'll have some kind of aggregate supply out here, I guess. So something like this is going to be aggregate supply added up in this case over those two firms. Is that clear? Okay, let me go ahead and work out the example for firms with Cobb-Douglas production functions. So in that case, what I want to do here is assume I want to give different Cobb-Douglas production functions. So I'm going to assume that this is the production function for firm I. So I'm going to have a sub I on the F. All the firms are going to face the same prices P and W, so there's no subscripts there. Hold on, let me give you a difference in the production function first. So y for firm I, call this y sub I, will be equal to a sub I times x1 I raised to the alpha 1, x2 I raised to the alpha 2. Okay, so that's the example. So output for firm I is equal to some firm-specific technological parameter a sub I. So one firm can have a better technology than another firm, and it'll depend on the inputs the firm chooses. Now that's going to, they're going to have the same exponents alpha 1 and alpha 2, just by assumption. That's going to give it a supply function, which is going to look like the thing we've got up there. Let me write this in a little bit simpler form. We'll have